Solenoid practice 3. In which figure is the compass needle pointing in the correct direction? We can eliminate that one and that one right away because those compass needles need to be pointing parallel or tangent to the magnetic field lines, and that is not what we're showing right there. So it's either this one or this one, and if we use our right hand rule for solenoids to figure out which end of the electromagnet is the north pole and which one's the south, we can see that if we have current going in this direction, we're going to use our right hand rule like that. And so this is going to be the north pole, this is going to be the south pole, and that compass would not do that. You can think of the south pole would be repelled from that south pole. I don't think that's the case. Let's try this last one. Once again, this is going to be the north pole, that's going to be the south pole, and that looks like a good looking compass right there. How about number 12? Draw needles on the 3 compasses to show the direction of the magnetic field. If we use our right hand rule for solenoids, we can see that the current is winding around the core in this sort of a direction. It's in the back, then it's in the front, then it's in the back and the front. So this is going to be the north pole, this is going to be the south pole. Our compass, if it's right directly axially lined up, it's going to point that way. Same thing here, this one's going to point in that direction, and then the field line will be going from north to south like that, and so this compass needle should point like so. What do we have here for number 13? Label the ends of the iron bar with N and S to indicate north and south pole. The current is going in this direction here, and if we use our right hand rule, that would suggest that we need to go behind the core and then towards the core. So I'm thinking that the north pole is going to be on that side and the south pole is going to be on the right there. Number 14, the solenoid at right consists of a bar of iron wrapped with insulated wire. When the switch is closed and current begins to flow, the iron bar will become an electromagnet, and the small bar magnet shown will experience a force of, will it be attraction or repulsion? Well, when we close this switch here, we're going to have a current that goes in that direction. There's our current. Using the right hand rule for solenoids, that would suggest that this is going to be the north pole of the magnet, and that's going to be the south pole, because our fingers are going to wind behind the core and then towards us in the front. So that's going to be the north pole, and those two are clearly going to attract. So I'm going to say attraction there. One more. In which direction will the electron be pushed as it approaches the electromagnet? We've got an electromagnet here. We've got an electron that's moving towards, and it's going to experience a force, and we got to figure out in which direction it's going to be forced. What we need here is we've got our current going in that direction, which allows us to figure out which one is the north pole and which one is the south pole, and that's going to be by our right hand rule. Sorry, this is a little bit hard, but the current is winding around in that sense. So that means near the top is going to be the north pole, and down there is going to be the south pole, which means where the electron is, the magnetic field lines are going to be directed straight downward. You see, I'm not going to draw all the field lines, but there's one of them that the electron runs into. And a long time ago, when we were doing these videos earlier, we were able to figure out in what direction a moving charge would experience a force if it was going through a magnetic field. And that was the pat-pat right-hand rule for positive charges. For negative charges, we had to use the pat-pat left-hand rule, which says something like this. You have your left hand, and the thumb points in the direction the charge is moving, and then your fingers have to point in the direction of the field lines. And you can see right now that my fingers are not pointing in the direction of the field lines. So I need to flip my hand around here like so. There's my thumb pointing in the direction of the electrons, and then my fingers are pointing down. And which way do we pat somebody on the back? This way, boop, boop, into the page. The magnetic force that this electron is going to experience is going to be into the page. And if we wanted to give some kind of justification for that, we could say the pat-pat right-hand rule, which is not an official name for a right-hand rule. That is a Bergman name for a right-hand rule, but it helps me remember it.